Welcome back to Java Internals Crashcasts. I'm your host Sheila, and today we're wrapping up our season on synchronization utilities. We've covered a lot of ground, and I'm excited to have Victor here to help us summarize everything we've learned. Victor, are you ready to dive in?
Absolutely, Sheila. It's been an incredible journey through the world of synchronization utilities in Java. I'm looking forward to recapping all the powerful tools we've explored.
Great. Before we start, let's kick things off with a quiz question for our listeners. Here's the scenario. You're developing a multi-threaded application where multiple threads need to wait for a set of operations to complete before proceeding. Which synchronization utility would be most appropriate for this situation?
Oh, that's an excellent question, Sheila. It really makes you think about the specific requirements of the scenario. Without giving away the answer, I'd encourage our listeners to consider the various utilities we've discussed throughout this season. Think about which one allows multiple threads to wait, and then proceed simultaneously once a certain condition is met.
Thanks, Victor. We'll reveal the answer at the end of the episode, so stay tuned, listeners. Now, let's start our recap. We began this season by exploring locks and conditions. Can you give us a quick overview of what we learned there?
Certainly. Locks and conditions are fundamental to Java's concurrency toolkit. We discussed the lock interface, which provides more flexible locking operations compared to synchronized blocks. The re-entrant lock, for instance, allows for more granular control over locking, including features like try-lock and lock interruptibly. We also covered read-write lock, which allows multiple readers to access a resource simultaneously while ensuring exclusive access for writers.
That's right. And if I remember correctly, conditions provide a way to make threads wait until a specific condition is met, similar to wait, and notify, but with more flexibility. Is that accurate?
Spot on, Sheila. Conditions allow for more precise communication between threads. They're particularly useful when you need multiple wait sets per lock, which isn't possible with the traditional object.wait and object.notify methods.
Great. Moving on to synchronizers, we covered quite a few classes. Can you break those down for us?
Absolutely. We explored 4 main synchronizers: Semaphore, countdown latch, cyclic barrier, and phaser. Each serves a unique purpose in coordinating thread actions. Semaphore, for instance, is great for controlling access to a limited number of resources. It's like a bouncer at a club, only allowing a certain number of people or threads in at a time. Countdown latch is useful for scenarios where one or more threads need to wait until a set of operations in other threads completes. Think of it as a starting gun in a race. Once the count reaches 0, everyone can proceed. Cyclic barrier is similar, but allows a set of threads to wait for each other to reach a common point before proceeding. It's like a group of friends agreeing to meet at a specific location before going to a movie together. Lastly, phaser is the most flexible, combining functionality from countdown latch and cyclic barrier, and allowing for dynamic party count.
Those analogies are really helpful, Victor. I can see how each of these would be useful in different scenarios. Now, let's talk about atomic variables. Why are these important in concurrent programming?
Great question, Sheila. Atomic variables are crucial because they provide a way to perform atomic operations without explicit synchronization. This leads to better performance in many scenarios. We covered classes like atomic integer, atomic long, atomic boolean, and their array counterparts. Essentially, these are special types of variables that can safely be accessed and modified by multiple threads without causing data races or inconsistencies.
I see. So it's like having a special type of variable that can handle multiple threads accessing it safely.
Exactly. It's like having a self-locking variable. These classes use low-level atomic machine instructions to ensure that compound actions, like read, modify, write, are performed as a single, uninterruptible unit.
That's fascinating. Now, we also covered some advanced synchronization techniques. Can you remind our listeners about those?
Certainly. We discussed StampedLock, which provides optimistic read locks for better scalability in read-heavy scenarios. Then there's Exchanger, which is great for pairwise thread coordination, allowing 2 threads to exchange data at a synchronization point. Lastly, we covered ThreadLocal, which provides thread-confined variables. essentially giving each thread its own private copy of a variable.
Those sound really powerful. Now I'm curious, how do developers choose which synchronization utility to use in their projects?
That's a great question, Sheila. The choice really depends on the specific requirements of the concurrent scenario you're dealing with. As a general rule, 1. Use simple synchronization, like the synchronized keyword, for basic thread safety needs. 2. Use reentrant lock when you need more flexibility in locking, like timeouts or interruptible locks. 3. Use read-write lock for read-heavy scenarios where you want to allow multiple concurrent readers. 4. Use Semaphore to control access to a limited pool of resources. 5. Use countdown latch for one-time synchronization events. 6. Use cyclic barrier or phaser for repeated synchronization points. 7. Use atomic variables for simple shared state that needs to be updated atomically. 8. Use StampedLock for advanced read-write scenarios where you want to optimize for read-heavy workloads. The key is to understand the characteristics of your concurrent problem and match them to the appropriate tool.
That's really helpful, Victor. It seems like there's a lot to consider. Are there any common pitfalls or best practices you'd like to share with our listeners?
Absolutely, Sheila. One common pitfall is over-synchronization, which can lead to performance issues or even deadlocks. It's important to synchronize only what's necessary and for as short a time as possible. Another best practice is to prefer higher-level concurrency utilities over lower-level ones when possible. For example, using a concurrent hash map instead of manually synchronizing a hash map often leads to better performance and less error-prone code. Lastly, always be aware of the potential for deadlocks when using multiple locks. Try to establish a consistent order for acquiring locks to prevent circular wait conditions.
Those are great tips, Victor. Now, before we wrap up, let's reveal the answer to our quiz question. The scenario was about multiple threads needing to wait for a set of operations to complete before proceeding. What's the most appropriate synchronization utility for this situation?
Great question, Sheila. The most appropriate synchronization utility for this scenario would be the countdown latch. It's designed precisely for situations where one or more threads need to wait until a set of operations completes in other threads. The countdown latch allows you to initialize it with a count, decrement the count as operations complete, and have threads wait until the count reaches 0 before proceeding.
Excellent explanation, Victor. To summarize our season on synchronization utilities, we've covered a wide range of tools provided by Java for managing concurrent operations. From basic locks to advanced synchronizers, these utilities give developers the power to write efficient and correct multi-threaded code. Understanding when and how to use each of these tools is crucial for any Java developer working on concurrent applications.
Absolutely, Sheila. The world of concurrent programming can be complex, but Java's rich set of synchronization utilities provides powerful tools to manage that complexity. By mastering these utilities, developers can write more efficient, scalable, and reliable multi-threaded applications.
Thank you, Victor, for all your insights throughout this season. And thank you, listeners, for joining us on this journey through Java's synchronization utilities. Next season, we'll be diving into concurrent collections, so stay tuned. If you've enjoyed this series, please subscribe to Java Internal's Crashcasts and leave us a rating. Your support helps us continue to produce high-quality, in-depth content about Java internals. Until next time, happy coding.